Alright, so today I'm going to be explaining another important paper with the title NODESIG, Binary Node Embeddings via Random Walk Diffusion. So diffusion, we have been talking about it in the past two videos. So this is the third video on diffusion, of course in the context of graphs and random walks. This paper is really important. So there is a motivation for this paper. This graph representation learning has become a key paradigm in network analysis with a plethora of interdisciplinary applications. As the scale of networks increases, most of the widely used learning-based graph representation models also face computational challenges. While there is a recent effort toward designing algorithms that solely deal with scalability issues, most of them behave poorly in terms of accuracy on downstream tasks. So in this paper, we aim to study models that balance the trade-off between efficiency and accuracy. So we propose NODESIG, a scalable model that computes binary node representations. It exploits random walk diffusion probabilities via stable random projections toward efficiently computing embeddings in the Hamming space. Our extensive experiments evaluation in various networks has demonstrated that the proposed model achieves a good balance between accuracy and efficiency compared to well-known baseline models on the node classification and link prediction tasks. This paper also is important. RAND-NE is one of the first scalable approaches which is based on iterative Gaussian random projection, being able to adapt to any desired proximity level. So this is a schematic representation of NODESIG, this paper, that first the weights of the random projection matrix are sampled, and then projection of the proximity matrix is performed via the weight propagation step. Finally, binary node representations are obtained by combining the signs of the projected values. So this is a proposed approach, random walk diffusion for node proximity estimation. In most cases, direct links among nodes are not sufficient to grasp various inherent properties of the network that are related to node proximity. It's highly probable that a network might have missing or noisy connections. Thus, relying solely on first-order proximity can reduce the expressiveness of the model. To overcome this problem, we directly leverage random walk diffusions, adopting a uniform random walking strategy to extract information describing the structural roles of nodes in the network. Let P denote the right stochastic matrix associated with the adjacency matrix of the graph, which is obtained by normalizing the rows of the matrix. More formally, this P matrix, this right stochastic matrix, can be written like this, defining the transition probabilities of the uniform random walk strategy. Note that the probability of visiting the next node depends only on the current node that the random walk resides. Therefore, node V sub j can be visited starting from V sub I by taking L steps with this probability. If there is a path connecting them, for a given walk length, we define this matrix M. So P sub L indicates the nth order proximity matrix, and each entry in fact specifies the expectation of visiting U starting from V. But by introducing an additional parameter alpha, M of alpha can be written like this. And this is importance factor. We call it, that is, alpha is the importance factor. Because high order node proximities can be captured using longer walks, where the impact of walk at different steps is controlled by this alpha. Random projection methods have been widely used in a wide range of applications dealing with large-scale data. We aim at encoding each node into a Hamming space. We consider the normalizing Hamming distance at the distance metric. So if you look at my first video on embeddings, I explained this Johnson-Linder-Strauss metric embedding, my playlist on metric embedding. You will see this important JO. So it can be written as this linear projection, simply can be written like this, and W is the projection matrix. And the entries of this matrix W are independently drawn from normal distribution. Okay, so we've got the binary embeddings. Now there is a theorem about that. Given any pair of vectors, what is the probability that they don't coincide, they don't become equal? These ideas are very similar to ideas of LSH, for example, locality sensitive hashing. They are very simple things that you can prove it easily. So we skip them. So the idea is that given a graph and transition matrix P, we want to find what is the embedding for each node. But during that, we calculate this iterative procedure, and P here is the transition matrix. And finally, we get the sign of R that we discussed. And these are data sets that they have used. And they did it for node classification, multi-label node classification. They compared for different, for example, node to vec. I've explained this in a different video. They compared baselines with NODESIG, which is the idea of this paper. And micro and macro, as you see, they compared different because macro is more precise. And we have introduced NODESIG and efficient binary node embeddings.